Okay, so for lab 2.5, doing Bernoulli's equation on this is the differential equation we were given. The first thing that I wanted to do was divide by x just to get the differential equation into our standard form that we're more accustomed to. Um, and so I did that, and I remembered that had I not known this was a Bernoulli's equation, I remembered that if I'm in a situation in which we have this form of a differential equation where n is not equal to 0 or 1, and so if your y's are in a situation like this where it's kind of not obvious how to solve using an integrating factor method, what you're going to need to do is substitute a v, this v right here, which is just y to the 1 minus n, and n being the highest power of your y exponent. So in this case, it would be 3. And so step 2 is to kind of find your v. And so I find my v just doing some algebra real quick. We get v equals y to the negative 2, just doing that little subtraction right there, which, you can just rewrite it as 1 over y squared. But we also want to know y in terms of v as well, because we're going to end up using that later. So just doing that out, I like to just write out like every little bit of algebra I do just to make sure I don't have any errors. And then I get y equals v to the negative 1/2. So that's the second step of doing this. And so these are important. We're going to use these throughout. It's a long problem. Then we're going to take the derivative of that y, which is now in terms of v. So we're taking the derivative of this term right here, which gives us this right here, the negative 1/2 v, chain rule obviously, so we're just subtracting out, becomes negative 3 over 2. And now this is important, it's dv over dx, the change of v over the change of x. And that's the whole point of this, that we're not really trying to use y's until the very end, because they're not, it's not something that's going to be useful to us. It's not necessarily linear, but we want to get it as close as possible. And so we sub everything in, or sub in all of our v's, which are, these over here, for these above y's, into this. So anytime I see a y, I'm just going to plug in that v. And with my dy dx, I'm just going to plug in that derivative I just took. So that, obviously, I'm removing the dv, or the dy dx, and putting it in terms of dv dx. The 1 over x is staying because there's no y, but it's being multiplied by what was a y. It's now v to the negative 1 over 2. And then that y to the third, we're just going to replace that as well, making sure to keep that exponent. But now it's still kind of not solvable, and so we need to factor it out and rewrite the equation into the standard form. I think it's form 6 in the book. I always mess up. I think it might be 2, but it's it's that one up there. So I'm just gonna multiply both sides by just to get rid of this. So just dividing this out. It's the same as just multiplying it. So I'm just multiplying negative 2v to the 3/2, right? Because that's the same as dividing. And what ends up happening, if I have everything, is you end up with going from that step to this step, you end up getting that v cancels out, that 1/2, this one right here, excuse me. This 1/2 v to the -3/2 gets canceled out because we're adding exponents when we multiply. So just explaining every bit of the algebra, sorry. And then we keep going, and this is now like in general form. This is something we like. This is something we've seen a bunch. So now we can use the integrating factor method, or the Shell's theorem, as the professor calls it. Identify this as the -2/x as your p of x. Take the integral e raised to that. We've done so many of these now that it's just pretty obvious and standard. And then we're just going to get that integrating factor of mu of x equals x to the -2, or 1/x². Multiply both sides by that mu of x, so it's the same as all the other integrating factor problems we've done. And we get this 1/x² dv dx minus 2/x³, right? That x², that x equals -2/x². We want to verify that this, and this all are part of a product rule, to make sure that we did everything right. And so if we take the derivative with respect to x of this term right here, we see that it is indeed present in what we just found. So we know that we're now doing things right. So we're on the right track. That's good. Then what you do is you're going to take the integral of just this term that we found earlier and that term. So we're not taking the integral of the derivatives of things, but we do keep the derivative in there just to remind us that they are indeed present in the solution. Do that and integrate with respect to x. I scratched it out because I had not, I didn't realize I was going to combine the steps, because once you write it out. But anyway, so you integrate now, and this is where the third page comes into play. Okay, so you integrate and you end up getting 1/x² times v. Pull out that constant, and it's just 1/x² dx. Do some just basic calc 2 to get what you need. And then now that you have, this is the answer to that integral, you get your plus c. Now we can solve for v. And then once we're done solving for v, we're going to plug back in that v equals 1/2/y. So we do that. We just do some more simplification, some more algebra. And we get v equals 2x plus cx², which is good. We then plug in v equals 1/y² on that side right there, right, to get that. And then we just simplify it back. So now we have y's equaling x's as opposed to v's equaling x's. So we're basically done here. I just figured I'd simplify more and just get the final answer. And it's in general terms, or it's the general answer, or part of the family of solutions, obviously, because we still have that c. So yeah, I'm also going to post pictures of all of this just so everyone can see how it went down. But yeah, ask questions, check my work, see if I did anything wrong, like I missed a negative or something like that. Yeah, thanks.